Our first presenter is Eric Williams. He has worked for Vector Corrosion Technologies for the past 2.5 years as their business development manager in the Mid-Atlantic area.
Thank you, everybody, for attending. Again, my name is Eric Williams. I'm with Vector Corrosion Technologies. I know I've worked with a few of you, and hopefully some of you, if you have any questions at the end, please let me know. Just a quick agenda for what we'll be going over. We'll doing a little bit for concrete repair, going over some corrosion basics, discrete galvanic anodes, what are they, why do we use them, and then proceeding to go through a couple of case studies, examples, and then wrapping up with some sustainability practices that we support. Current state of repair, I don't think I have to tell everyone in this room about how much corrosion issues face, and it's pretty much the leading issue that our nation's infrastructure is facing. It estimated about 18 to 21 billion dollars in corrosion issues throughout our nation's infrastructure. And I always like this last point on there where it's stating that about 50% of the repairs that are done are actually lasting to their full life and capability, which is a really nice way to say that 50% of repairs are actually failing before they reach their life. One of the biggest issues that we see, and the reason for that, is the roadway salt that's being used throughout the country. I think you can see really right where the late 60s, early 70s, where our nation's infrastructure was really being built up, and a lot of our nation's bridges were being built. Obviously, the salt consumption and the salts being inundated there have jumped significantly, even at around the year in the late 90s, early 2000s. So a lot of these structures are being inundated with chlorides and salt, and especially here in the Northeast where our winters can get pretty rough, and we're constantly putting these down on it. Just some pictures where I'm sure a lot of you have seen familiar with some of these photos. A lot of concrete deterioration and corrosion issues due to the ingress of chloride throughout. Some industry resources and some of the places that we're pretty involved in. I don't know, a show of hands. Anybody member of any of these, familiar with them? ICRI, ACI, I see a couple hands going up. NACE, so we're pretty heavily involved in a number of these, and they're really great resources for a couple of different things. They go through a lot with concrete repair and proper concrete repair techniques. A couple of examples here is your surface preparation. This is through the ICRI, so you can actually go through and they'll give you specific these little tablets that show you how you're supposed to exactly have your concrete surface prepared for whatever type of repair that you're doing. So if you're doing this and actually specifying, hey, this needs a surface profile of 6 or a 7, well, what does that actually mean? You can actually give a physical photo of that for whoever is going to be doing the repair, which I know some people really appreciate. Some more things through the ICRI. I know people have probably seen some repairs that maybe people have done like this or maybe like this. They just go through basic, hey, we want nice square, clean saw cuts, making sure that we have 90-degree angles when we are doing our saw cuts as well. Proper cleaning not only of the reinforcing steel behind it as well. So there's just a number of these different types of things on there that are really useful when you're going through and doing your repairs. ACI, there's a lot of different ones, different codes. I know ACI Repair Code 562 is one of the repair codes that have been used not only in buildings, but some of the owners, DOTs, have started to bring that on as well. So, number of different types of codes and just resources on some of these members or these memberships that you can take advantage of. Hopping right into really corrosion and where is it coming from? Chlorides, obviously, we know marine environments, de-icing salts, some chemical plant issues that we see. Carbonation of concrete, same kind of concept as chlorides, except carbon dioxide is dropping the pH level of our concrete, moving it more towards an acidic base, which starts a corrosion cell as well. Typically, we're seeing those in much older structures or anything with low concrete cover, you'll see carbonation of concrete. What it really comes down to is both of those will break down that natural passive oxide layer that's surrounding steel when it's in concrete. And that's going to cause our corrosion issues. So I went over sources of chlorides. I think we're all pretty familiar with those. One of the big takeaways from this slide as well is chlorides are never consumed. Once they're in your structure, they're always going to be there unless we remove them in some way, shape, or form. So even by covering them up or doing something like that, they're still going to be in there and causing issues for our reinforcing steel. This is a corrosion cell. I always like to just review this because this is what all of the galvanic principles that we'll be talking about are based off of. This is what's happening when you have a corrosion or chlorides or carbonation coming down to your reinforcing steel, and it'll be breaking down that natural passive oxide layer that naturally surrounds steel when it's in concrete. We talk in terms of electronegativity when we're talking about corrosion, because what is steel corroding, right? It's just an iron ore that we placed a lot of energy to, and then that energy is being given off and reverting back to an iron ore. So that energy is being given off in the form of electrons. So when electrons are being given off, those are negatively charged. And as that area starts to corrode, it's called an anode. An anode's where the energy is leaving from in a corrosion cell. So your anode will start to form. Those electrons will be given off. They'll flow down some metallic pathway. That steel could be from here down to here. For this illustration, we're going to use the bottom mat. And then a cathode will form, or a cathodic area. The cathodic area will accept those electrons, and then hydroxyl ions will go back and forth between some type of electrolyte. Well, when concrete, that's our electrolyte. If we were working in pipelines, the soil would act as our electrolyte. In marine environments, the water. Those hydroxyl ions go back and forth, then you get Fe2O3 or rust byproduct or corrosion byproduct that forms around your steel. And that's what can expand up to 10 times its natural size, and that's where you're getting your cracking, your spalling, all those nasty things that happen to our structures. Essentially what you're looking at is the same electrochemical process that's in a battery. You have your carbon rod on the inside, your zinc shell on the outside, you're putting it into whatever device you're putting it into, and that carries that current and causes the device to work. I always like this picture. It's a great picture of, this is a patch that we opened up. We didn't do anything, we didn't clean the bar on the right or the bottom left. Really all it is this great illustration of here's your anodic area here where you're having your corrosion issues, and then here's your cathodic area right next to it. So you have a real good illustration of showing where your issue is in terms of corrosion, and then what's actually technically being protected by that area of corrosion is the adjacent bar right next to it. Patch accelerated corrosion, or halo effect, ring effect. I don't know if a lot of you are familiar with this, but when you're looking in terms of corrosive activity, say we had a patch right here, and then the next thing you know, you have a patch that's starting next to it, and next to it, and next to it, and so on and so forth. Well, what's happening is when you're doing your patch repair, you could be doing everything correctly, right? You're milling down, or you're taking out the bad concrete, you're putting in a good material, but it's bonded well, all those things. What happens is essentially you passivate the steel in that patched area. So in that patched area, you're back down to a nice passive state where steel wants to be about negative 200 millivolts in that state. The surrounding areas where if it's still more electronegative because of due to chloride contamination or carbonated concrete, whatever the case may be, that potential difference between that area within your patch and that area outside of it, you have essentially flipped your anodic and your cathodic site. So what that's going to do is start the whole process over again, and that's where you get that ring or that halo effect. That's what's causing it. One way that we go and help to prevent against that ring or that halo effect is the use of galvanic anodes. Galvanic anodes, the ones that we use, you're going to be using zinc. Zinc is much more electronegative than reinforcing steel. So anytime you put two dissimilar metals together, the more active metal will corrode first, rather than the corrosion happening at the more noble metal. So by tying on these galvanic anodes, they're zinc cores with a high pH mortar around them to keep the zinc active, and then that'll help not only protect your reinforcing steel within your patch, but all that surrounding contaminated concrete that's more electronegative. So that's going to help stop or prevent that ring or that halo effect that you may have seen in some of your repairs. They're pretty simple and straightforward to install. Like we talked about earlier, you want good square, clean saw cuts, nice, clean reinforcing steel. You do need steel-to-steel connection for these to work. So you'll literally be tying them directly onto your reinforcing steel like this. And you want to be able to test that not only you have a good connection from your anode to your reinforcing steel, but also these bars over here, you want them to be continuous or touching in some way, shape, or form as well. Because that's going to allow the current to go from this galvanic anode here, not only to this surrounding steel, but it'll travel down these bars as well and protect the steel up here as well. Pretty simple to test for. You get a multimeter, you can put it on ohms or millivolts, and you just want to see 1 ohm of resistance or less, or 1 millivolt or less, and you know you have a good connection. If these bars weren't touching for whatever reason, there was a space, whatever, you could take a rebar tie or something like that, tie them around, make them electrically continuous, and move forward. Again, you want these anodes around the adjacent of a patch. You want to protect that interface between old and new material. I always like to kind of point out as well, for these galvanic anodes. These aren't going to provide structural protection all over, the ones that I'm speaking about here. You're really going to get that perimeter of the area around your patch where you're going to get most of your protection. If you had another element or another lane down here, it's not going to do anything down there. Zinc can only throw current so far when it's in concrete. A couple case studies and where we've used some of these different galvanic and pressed current cathodic protection solutions. This is some of the galvanic anodes in a pre-stressed box girder, where obviously they had some drainage issues. I believe that really what was happening is water was just coming down and pretty much eating away the face of that girder. And this was I believe it was in upstate New York, where they were trying to get another about 15 to 20 years out of this bridge, because if they didn't, I think the detour was about 25 miles, which would have been really crappy for this guy right here. So our solution for them and to help them out was our drilled in galvanic anodes. So rather than having to open up an entire patch and use these type of, and do it that way and get rid of all these concrete, literally what they're going to do is core into specific areas where they want to target corrosion protection and run them in a series and attach them that way. You can see here are the drilled holes where they put in these type of anodes for the protection of the steel, and then they're just going to do a saw cut in between them. Between that saw cut, they'll lay wire and attach each one of these anodes individually. So you do need a steel-to-steel attachment for these to work, but you can attach them at one end of the series and another at the other end for redundancy, because if we lose one connection, then we have a whole string of anodes not doing anything. All they do then is they'll grout everything over, and that's what it looked like when it was completed. Real nice that for these galvanic solutions, you do not have to monitor them. There's no maintenance that's required. You can kind of put them in there, set them, and forget about them. You can see here they did want to monitor these, so they did put in some monitoring boxes so you can easily go up. Anybody from either the engineer or ourselves or the DOT can go up and say, okay, these are still throwing current. We know that they're still working, and move on. But again, they're pretty simple to monitor, but you don't have to. Which is one of the nice benefits of using galvanic protection. Galvanic encasements, this is more we talked about for targeted protection for drilled in type anodes. Maybe we just have some isolated areas we have to protect, but what if we have entire structural elements? And that's what pretty much we do with galvanic encasement. You're doing maybe an overbuild or milling down to the face or getting to the reinforcing steel and protecting larger elements of the concrete. So in here you're looking at different columns that we've done it. Some of these have been pretty rough shape. You can also use where we've done it in you can use it in a concrete jacket, or in this case they decided to put PVC forms around the galvanic anodes or the galvanic encasement to help protect it as well. So a couple different options you have there in terms of protection with that. Encasement of beams, a lot of substructure elements we've done with these types of galvanic encasements. I don't know if anyone gets into a lot of accelerated bridge construction or rapid bridge replacement, but that's where these type of anodes really come into play, because you can match the life of what you just did up top and having to replace a deck to maybe the substructure below, and you can match the life of that bridge up. Some more where we've done them in some abutments. There's a good illustration here of where we've done some projects in Ohio where they were going to do an overbuild. They dialed in some new epoxy coated rebar and then placed the galvanic anodes on that new cage of rebar, and then they will tie all those galvanic anodes back into the existing reinforcing steel. So this is a good illustration of it here. You can see the anodes, or the encasement, is these long red type anodes, and then the new cage of rebar. You can see that they have everything wired back into the existing reinforcing steel, because again, that's what they're trying to protect. It's hard to see, I don't know if you can see it from this photo, but then they ran some wire up and we've been monitoring these ever since. We thought initially this was our first project we did with these back in 2005. We estimated that we'd probably get about 20 or so years out of it, and it looks like it's going to be closer to 30, 35 years for the life of these anodes. That's what it looked like when it was completed. So we've been monitoring it, working with the DOT that we've done this with, and they're still throwing current and working pretty well over time. So moving on along to some of the marine environments, and similar to what we talked about, instead of encasement though, they're more doing for pile jackets. There's several different times or kinds depending on where you are and how much protection you need. So there's zinc mesh jackets that we require for the salt water. It needs to keep this zinc active, so you'll put some stay-in-place forms, attach the zinc, put some stay-in-place forms around it, and allow that salt water to seep up and keep that zinc active. These are more for just tidal zone protection, because that salt water can only leach so far up or seep so far up into the concrete. For zinc mesh, that's kind of the tidal area, or the tidal zone is what we're looking at. If we needed higher protection, we are able to do that, but you're going to look at using a wicking anode is what we call it. So there's a fabric around a zinc core. Same concept as the zinc mesh jackets, where you're using salt water to keep it active, but it works kind of like an old school lantern, where it's going to soak up that salt water at a higher elevation, so you're getting higher protection. You're getting protection at a higher elevation. So this will help when if you have some atmospheric chlorides or things like that at a higher elevation along your pile, where it's going to help protect that, keep it intact. There's also some different options for the forms themselves. I know in the past we've used a lot of fiberglass. One thing that we've been offering is out there now is PVC. The contractors and people that we've worked with really like using the PVC. They snap together really easily in the field, and they're easy to maneuver and work with. They ship a lot easier as well, so the contractors are really appreciative of that. And they also have some bonding advantages as well. They work really well, they're a little less expensive, and yeah, we've been getting some good feedback. But you can still use either one, and just depending on the need for the project. And then last but not least, for marine environments is, well, we talked about saltwater environments, the saltwater keeping the zinc or the anodes active. Well, what if we're in brackish water or fresh water or even dry land in those types of cases? Well, there are areas where obviously if you need that, we do have self-activated marine anodes where you don't need any salt water. I'm actually working on a project with Virginia right now where they're worried about zinc contamination because they're worried about baby oyster beds. They decided that they didn't want any zinc in contact with the water, so they decided to use a self-activated type jacket in order to keep zinc from going into the water and stopping any environmental concerns. And obviously down below there I failed to mention bulk anodes. You can use those, attach those at the bottom around your mud line. That's going to help protect and stop corrosion for underwater issues. And then there's an example of a project we did down in Florida where they used a number of these different type of self-activated jackets throughout in the splash zone areas. So again, it's not being constantly inundated and enough to keep activated through the salt water, but self-activated will be good for this type of application. Everything that we talked about so far has been more geared towards galvanic protection, the use of dissimilar metals, one corroding first to sacrifice itself versus the other. This one here, though, is impressed current cathodic protection, or ICCP. Impressed current cathodic protection works really well for something that you may want to last a really long time. The anodes, the reason that we use some of the anodes that we do, you can see that we have some MMO, some mixed metal oxides, as well as some titanium ribbon and titanium mesh. The reason that we use those is the anode, technically it corrodes, but it takes a really long time. So you can get some really long life out of impressed current. Now I know some people who I've spoken with have had bad experiences with impressed current, mainly for the reason that it has to be monitored and maintained. If the owner or whoever may be wants to use impressed current, we would never recommend to use it without some type of monitoring or maintenance to go along with it. Now the nice part is we can do that remotely now and put modems and data loggers into rectifier cabinets, so you're alerted to whether a power goes out or it gets struck by lightning or a wire gets cut, or we've heard stories where people, I don't know what this is, so they just turn the power off and they don't have any power going to their system. So impressed current works really well, but it has to be monitored and maintained to make sure those electrical components and you have current going to the system. The next evolution of impressed current system, and we went over what's galvanic, what's impressed current, is using a hybrid or a fusion type system of both of them. So what this is, it's a combination of not only an impressed current system, but a galvanic system all in one. What you're looking at, so we went over corrosion and what that is, and what a fusion or a hybrid system is has its own self-contained impressed current cathodic protection in the anode itself. So what that's going to do is phase one is shoot a lot of current quickly in order to passivate the steel so it's in that non-corroding state. Doesn't require outside power source or anything like that. It's all contained within the anode. Then, as that first stage of the anode runs and passivates the steel, it automatically switches over to the second part, which is a galvanic piece, similar to the anodes that we talked about earlier. So you're going to get kind of the benefits of both worlds, where you're getting an impressed current where you can control the amount of current going to the steel initially, and then the maintenance-free capabilities of a galvanic system down the road. Here's what it looks like. It looks very similar to the targeted protection anodes or the drilled-in type cord anodes that we use. One of the projects that we're doing it on right now is the Arlington Memorial Bridge in Washington, D.C. This is the bridge that connects the Arlington Memorial Cemetery to the Lincoln Memorial. And I know there was initially when they started looking at this project, they wanted an impressed current cathodic protection system throughout the whole bridge. They reached out and got a couple of estimates on that, and FHWA, or Federal Lands, came back and said, well, is there anything else we can do? We came back to them, and this was our solution for them. So you can see here where we went through, and rather than having to do a global system throughout the whole structure, you're going through and targeting specific areas where you have corrosive activity, putting in these type of anodes. They're going to monitor sections of them, but again, you don't need outside power sources or continuous monitoring of these anodes. They pretty much work on their own. Last but not least is if you have a structure where you really don't want to change the aesthetics to it, maybe it's historic in nature or historical and you want to keep it intact. And one of the things that we've done as well to help extend the life of these types of structures is electrochemical chloride extraction. Essentially, it's an impressed current system on steroids where you're running a lot of current through the steel in order to literally extract the chlorides and reset the life of the concrete. What you do is you'll set up a temporary anode on the outside of the structure. We usually use a welded wire mesh, and then you're blowing in some type of conductive media or a temporary electrolyte to help the current go from your structure to your temporary anode on the outside. You'll hook up a direct DC power source, so your positive is going to go to your anode and your negative to your reinforcing steel. And as that negative current is charging and going into your reinforcing steel, chlorides are negatively charged ions. So it's actually going to sit there and pump that current throughout the steel where you have it and push it to that temporary anode on the outside, extracting the chlorides. And what that's going to do is not only extract the chlorides out of your structure, but it's going to raise the pH level of your concrete back up to an acceptable level, and that natural passive oxide layer is going to be restored around your steel. So it's almost why we say it's kind of like resetting the life of the concrete for your structure. One of the places that we did this was the Vine Street Expressway in Philadelphia. They were replacing a bunch of the bridge decks on top, and what they decided to do was the abutments were still in pretty good shape, but they knew the life of those new decks were never going to match the abutments below. They did them on a number of the abutments. You can see here, here's what it looks like when the welded wire mesh is installed. It's the example of them blowing in that temporary electrolyte to help carry the current from the structure to the reinforcing steel. You wrap everything up, you keep it moist. That helps with the conductivity of the current, as well as people like that things don't catch on fire. They zone, subzone everything out, make sure that everything is monitored constantly through clamp meters and things like that. Here's a good photo of what it looks like when it's opened up. So you can see the wire mesh is corroded to all hell, and you have a lot of corrosion byproduct that you're actually pulling out of the structure at the same time. This all is temporary. It all gets broken down, washed down. You put some type of sealant or sealer on top of it, and you're good to go. A lot of things that go into construction is raw materials and the use of obviously everything that goes into it. I think you can see on here that about 40% of solid waste comes from construction and demolition. And there's a number of different things that for every 10,000 cubic yards of concrete that we save, we can keep a lot of stuff out of landfills. So one of the things that we've partnered with is we have a website that we're part of and an alliance with other different companies, and it's wesavestructures.info. And on here, hopefully you can see it, it's actually an environmental impact calculator where if you put in the amount of cubic yards, and for our Canadian friends, we always have the metric there as well. If you put in the amount that you're actually going to be saving by doing some type of rehabilitation, it'll spit out all of this information and showing you the impact that you're having. I know some people who have kept this within some of their presentations or with some of their proposals to show not only that they're doing the right thing from an engineering standpoint, but also the right thing from an environmental standpoint as well. Open it up for any questions. Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.